And we're back. Welcome back from the weekend and happy Thursday. Today, we're going to pivot our conversation to start our discussion on so-called continuous distributions. But before we begin, we'll cover some administrative bits. The reading, we have added new reading by November 12th. Make sure you're getting this done on Chapter 4 on continuous distributions, sections 4.1 through 4.2.4. It's not a lot of pages 75 through 92. As usual, please make sure you're keeping on top of the reading. So, when we think about certain other quantities, stochastic quantities, we think about all sorts of systems, and these systems, we can make measurements over them, and the aspects that we measure from these systems are so-called inertial quantities. Let's take a look at light and heat. Here we have a candle. A candle is a tiny bit of light as measured by lumens or photon energy, and the sun is a lot of light measured by lumens or photon energy. Likewise, you could talk about the heat from a single candle. Yes, a candle will give you some heat. It's a little bit of heat, and heat is nothing more than thermal flux, thermal energy. And the sun gives you a lot more heat. So here we have a little bit of light, a little bit of heat. Here we have a lot of light, a lot of heat. Let's take the greatest basketball player ever, Michael Jordan. Now, when we measure time, we have Michael Jordan when he was in high school. We have Michael Jordan when he played in college for UNC Chapel Hill. We had Michael Jordan was early in his career on the Chicago Bulls. We had Michael Jordan later in his career, and then we have Michael Jordan very recently. And so here we have time, and when we think about time, we can measure that in minutes, in seconds, in hours, in days, or in this case, in years, or maybe different decades over the years. We can also, if I draw your attention to this bottom figure, we talk about pressure. Now, pressure, we might have pressure coming from a pipe, and if that happens to your pipe, you might want to call a plumber or some other heating ventilation expert because you're going to have some problems. But that's only a certain amount of pressure, relatively small. And then if you go to visit Yellowstone Park, Old Faithful Geyser, well, that's a lot of pressure. So here we have a small amount of pressure, a large amount of pressure, and you can think about all sorts of pressure measurements or values in between. So certainly if you're dealing with certain systems, well, the pressure that you measure for a pipe, it might be high, it might be low, and even for a constant pressure on a dial or gauge, it's going to fluctuate a little bit here and there over time. And so some types of stochasticity deal with these so-called inertial quantities, and we'll get into that, what inertial means in a moment. And so we have certain quantities, and these are often physical quantities like pressure, time, temperature. We might even add distance, position, velocity, acceleration. Now, all of these values share something in common. These values that we might measure in terms of stochasticity from some system, they can all take on values from the set of real numbers. And so these are also inertial. What does inertial mean? It means that the future value is dependent on the present value. So if you think about it, if you have, for example, a Cartesian plane, or maybe it's a room, and this room, you mark one spot in the room by origin, and you measure one position in the room as your y-axis, and the other position in the room as your x-axis. So at some moment in time, time zero, let's imagine you had somebody's position was marked as falling coordinates along x at time zero, x naught, and y at time zero, y naught. So there's the person. Person is at position x naught, y naught at time t0. So at the next time instant, time t1, well, that person just can't arbitrarily be way over here at time t1. That just doesn't happen. They have to be at their previous location or present location plus or minus some amount delta along the x-axis and the y-axis at their future location. So inertial means that your future value is dependent on present value. You don't shapeshift and all of a sudden, in an instant, go from one position to some other position all the way across the room. That doesn't happen. You go through intermediate positions along the way over time. The future value is dependent on the present value. And so all of these are inertial, and they're also quantities that traffic in measurements that are drawn from the set of real numbers. And so the set of real numbers is interesting. And when we think about the set of real numbers, one of the questions then, if we're talking about probabilities as being the outcome of some measurement, some observation, a natural question that you might ask is, how many values do we have in the set of real numbers? Well, it's infinite. Not just infinite, more correctly, it's uncountably infinite. And so, yes, it's infinite, but what in the world does this uncountably part refer to? So let's take a look at this and visualize it. And so this uncountably infinite means that this thing is so infinite, so big, that you can't even number them. You can't draw a one-to-one correspondence with the individual elements of the set of reals. And the reason for that, and I'll illustrate this, is that for every two real numbers that you can find, no matter how close together they are, you can always find a large number or infinite number in between them. And so it never bottoms out. You can never identify, for example, like in a set of evens, an even number 2 and the next even number 4. There's always an infinite number between every two elements of the set of reals that you can imagine. So let's visualize the real number line. And in the center here, we have 0. That's a real number. And it extends off to positive infinity in the right-hand direction, right-hand side. And it extends off to negative infinity on the left-hand side. And so along the real number line, we've marked the integers. And so here we have the negative integers, -1, -2, and so forth, going off to negative infinity on the negative side. And then we also have the positive integers, 1, 2, 3, 4, etc., extending off towards the right to positive infinity. And so it just so happens the integers, we mark them in the set of reals, and these integers, they are countably infinite. We can say, all right, label 0 with a 1, and then alternate. This is 2, this is 3, -1, this is 4, this is 5, and so forth. So absolutely, the set of integers going from negative to positive infinity are countable. But you'll notice here, when we mark the set of integers going off from positive to negative infinity, we still have a lot of space in between them, an infinite number of space. So there are countably infinitely many of the integers going from negative to positive infinity. But this doesn't even begin to provide coverage to allow us to identify a particular element of the real set of real numbers. So how do we identify some number A from the set of reals? How do we do that? Well, we kind of can't do that. All right, so let's try some other approach. We can take an interval, and these intervals we're going to draw by carving out those parts of the real number line corresponding to segments that are between successive integers. And so here we have an interval, closed interval, on the real number line, including the endpoints between 0 and 1. And so we can take each element of the set of integers and look to its next neighbor. So for -1, it'd be 0, 0 would be 1, and compute or identify, segment off the closed interval between each integer and its neighbor. We can identify each integer, we can identify its neighbor, and so we can absolutely identify these intervals. Now, of course, because we can identify each integer and its neighbor, we can count them. And because we can count them, that means there are countably infinitely many of these intervals as well. So if we take that partitioning and grab one of these intervals, yes, we can count that. There's the first one, there's the second interval, there's the third interval, there's the fourth interval, and so forth. So, all right, well, let's try these intervals. We count it. So let's take that first interval on the real number line between 0 and 1. Now, if I gave you that interval, you could then take that interval and chop it up into an infinite set of subregions. So you can say, okay, well, take halfway here, and then halfway here, halfway there, and halfway between each of those, and keep doing that. And so you can identify a countably infinite set of numbers that are within this region on the real number line between 0 and 1. Okay, well, then if you did that and you gave me two of those segments or points along the partitioning of that segment, I can then take one of these. And if you give me this number A and this number B, I can subpartition between A and B, that interval, yet again, an infinite number of times, countably infinite. Absolutely, I could do that. Now, of course, I do that again, and then I do it again, and then I do it again. And so I can keep subdividing, and every time you give me 2 points for an interval, I can give you a countably infinite number of subpartitions, and you do it again and again and again and again and again. And so you can keep subpartitioning an infinite number of times. And so what this means is, because you never reach the point where you have a single element of the real numbers that you can identify, this infinity is so big that you can't count it. You can't assign a 1, a 2, 3, 4 to each one of the individual elements from the set of reals. You can't find that one-to-one correspondence with the naturals. And so this particular infinity for the set of reals is so big, you can't even count it, because you can never subpartition it to the point where you get down to the individuals. For example, in the set of evens, you can get down to a single even, 2, where the next one is 4. But you can't do that with real numbers. We can keep partitioning, and never reach an individual element of the set of real numbers. So that's what uncountably infinite means. And so towards the beginning of the semester, we talked about a system called probabilities. And we said it allows you to quantify or measure this idea of when can I see you again? What is the frequency of occurrence for a particular outcome? And you have many different outcomes that you can observe from some trial. And so we talked about this system called probability. And in our discussions, we talked about sample space. And it was the sample space that listed the set of all possible outcomes, and the cardinalities of these sample spaces were finite. So for omega dirole, we said that was a sample space consisting of those outcomes 1 through 6, and we said the cardinality of omega di is equal to 6, and that allowed us to compute the probability for a particular outcome. Now, of course, this idea of counting the sample space, if we're trafficking in some quantity, some observation that is a real number, well, we can't count them. If you can't count them, what are you going to do? So typically in mathematics, if something violates the previous assumptions, well, you kind of repair the damage. So rather than invent a whole new system for random variable probabilities that are uncountably infinite in their sample space, let's use the old system that we had for the countable case and just repair the damage that occurs, or repair the issues. Okay, so let's take a look at some beginning parts. We have these Kolmogorov axioms, and these describe what it means to be a probability. It says that a probability is a real number. In particular, this probability is drawn from the closed interval between 0 and 1 on the real number line. At this juncture, we know this. And the probability of a particular event is non-negative. It's always positive or 0. Well, that's important. The second Kolmogorov axiom said that if you were to take the probability of all the possible observations, that's equal to 1. Now, of course, if all possible observations are uncountable, it still has to be equal to 1 if we're going to talk about a probability of some random variable that's going to take on a real value. And so that was our second Kolmogorov axiom, this law of total probability. And next, we had what we called sigma additivity. It says that if you have disjoint events and you have a complex probability formed by taking the union of those simple events, well, the probability of that complex event is nothing more than the sum of the individual probabilities of the simple events. And so it says that probabilities of mutually exclusive or disjoint events sum, and it gave us a way to construct complex events. Like a set of evens is the union of 2, 4, and 6 for the die roll, for example. And so some corollaries to the Kolmogorov axioms, these are things that follow from our definition. The first corollary, one of them, gives us a numeric bound on what the probability is. Because law of total probability says they all sum to 1, and the first axiom says that it's at least 0, that means the bound on a particular probability for any event is in the interval between 0 and 1. So that gives us our numeric bound for probabilities. Likewise, we also have probability of the empty set is 0. So the nothing event has a 0 probability. Nothing will never happen or ever happen. So this gives us the probability of the empty set. And then we also have this idea of monotonicity that follows from our third part about how you construct, our third axiom, about how you construct complex events. And so here, if you have two events, A and B, and A is within the set B, then the probability of A is less than the probability of B. So let's say you said A is the set of events, all the evens for the die roll, less than 6. And then you had B is all of the evens. Now A, all the evens less than 6 is event 2 and 4. Evens, all the evens is 2, 4, 6. So here we have A is a subset of B. There's A, there's B, that's true. And so the probability of A is less than the probability of B. Absolutely. And that follows from this sigma additivity, or this construction of a complex event. Event B is nothing more than the union between event A with that singleton event 6. And therefore, if we were to compute the probability of B, that's nothing more than the probability of A plus the probability of that singleton 6 event. And so this is called monotonicity. And so let's look at how you measure this. Now, remember, we said the law of total probability from the discrete countable case said if you add up all the probabilities for all instantiations of our random variable or measurement, the probabilities all added up for every possibility is equal to 1. Now, if x is uncountably infinite, well, that means if you were to add up all those probabilities for that uncountable number of outcomes for x, that sum of all those probabilities is going to equal to 1. Now, this is an important notation. I cannot do this. I'm just writing it out to demonstrate the idea, but this is a severe abuse of notation. Just by having this notation x1, x2, x3, etc., up to x4, this means I can count it because I can list out the first one, the second one, third one, but I can't do this in practice. So let's acknowledge and establish this is an abuse of notation. This is just to demonstrate the idea of why total probability is broken for the uncountable case. And so you can't write out x1, x2, 3 because it's uncountably infinite. I can't really do this. But if you think about what total probability means, you have one unit of total probability mass. And if you have an uncountably infinite number of possibilities, if you were to put them all together, imagining that if I could sum them together, you're basically taking that unit of probability and you're spreading it out over each one of the individual probabilities. So I would have an uncountable number of divisions, if you will, of this unit of probability. So it's almost like, imagine if you had, a jar of peanut butter, and you wanted to take that jar of peanut butter and you wanted to divide it among an uncountably infinite number of people. Well, if there are way too many people, that peanut butter is going to get really, really thin if you have a larger number of people to spread it around between. Now, again, I cannot write this because our variable of consideration, x, is from the set of real numbers. But if I could, that unit of total probability, the sum of all of the individual outcomes, I'm spreading out that unit among an uncountable number of alternatives. And so if I take one and I divide it by something really, really big, uncountably really, really big, well, that's going to be effectively 0 in the limit. And of course, this limit, as n goes to infinity, this is an uncountable infinity. And so that means then the probability mass associated with a single element of the set of reals, that probability is going to be 0. Uh-oh, now I have a problem. This means that the probability of a single outcome is 0, and I never observe anything at any time. I've broken my probabilities. And so in this case, a real valued measurement or observation breaks all the rules of probability that we've talked about, because they don't sum to 1, because an individual is 0. If I'm summing together things that are 0, it's 0. And likewise, the probability of a single real value is 0. So nothing ever happens. So not only does nothing ever happen, this sums to 0. Uh-oh, probability is broke. And so what are we going to do to fix this? Well, I had a little bit of a hint when I gave that description of what uncountably infinite means. Now, let's just rewrite the Kolmogorov axioms that define what a probability is, just for convenience sake, so we don't have to flip slides back and forth. But these are our axioms. And instead of the mass function, probability for a single outcome, this is a mass function, probability mass function, or PMF, that we talked about in the countable case. And instead of the mass function, we're going to use the cumulative distribution function, or CDF. Now, to remind you what the CDF was in the book, they used capital F of x, and that's nothing more than the total probability for all of the values of random variable x, that's random variable x, from minus infinity up to and including a particular value x. And so because the probability in the uncountable case for a single alternative is 0, well, at the x equals 0 point, it's 0, so we can just rewrite that as probability of random variable x is less than x. And we can just drop that equal part of less than equal to altogether. Okay, so we're going to use the CDF. And in essence, what we're doing, we're taking multiple elements or regions within the real number line, and we're treating that as our unit of consideration when we compute the probability. And this is exactly what we're going to motivate. Okay, so we have the CDF, and now we're going to talk about a density function. A density function is going to be the derivative of the CDF. We have the CDF here, which is a cumulative construct, and then the density is its derivative. So what does that mean? So if I have some region, and that region is a set of values along the real number line, the density says if I go from minus infinity up to some value x, and I add together all the probabilities, well, the density says how does it change as I go in that direction from minus infinity up to x. And so from now on, when we talk about the probability associated with a real number observation, or so-called continuous random variable, we're going to talk about the density, how that probability is spread out from minus infinity along the number line, real number line, up to a value, instead of the probability associated with a single point, because probability of single points on the real number line breaks probabilities. Okay, and so henceforth, when we talk about continuous distributions, we're going to talk about their densities, and a density is nothing more than the derivative or the rate of change of this cumulative distributions function, our CDF. Okay, so there's the key insight. Now, back when we talked about a definition of what uncountably infinite means, we started out and said, I can't count the individual real numbers, but I can count these regular sized intervals between an integer and its successive neighbor going in the direction of positive infinity. Its right-hand neighbor. I can count those. And so if we were going to count these, guess what? That's a region. And a region can be calculated as saying the probability that random variable x takes on a value that's less than equal to some value x. And I can use the CDF to construct an arbitrary region. So let's take a look at that. And so let's take our number line and let's imagine we had two equal pieces for the real number line. We know 0 is quote unquote in the middle, and we can go off from 0 to positive infinity to the right, and we can go off to the left to negative infinity on the left. And so here we have two equal sized regions. They're infinitely big. They're both uncountable, but I know each one comprises half of the real number line. So in that particular case, there are countably infinitely many of these regions. There's the first region, there's the second region. So I know I have two events. There's the set of events corresponding for the observation of my real number being 0 to positive infinity, and then there's the set of observations of my real number being from 0 to negative infinity. So if I have two things intervals that I'm talking about, the probability is going to be spread between each one of those equally. So that means the probability of each one of these is half. So the probability of this region is equal to 0.5, and the probability of that region is also equal to 0.5. And so certainly I can talk about these regions because I can talk about my CDF, and I can count regions, but I can't count the individuals. So that's why we have CDFs, and we talk about densities, and we can use the tools that we already have from prerequisites from this class, tools from calculus, in order to construct complex sets that consist of not individual real numbers, but intervals of real numbers. Okay, and so because we can count our intervals, this gives us a way to traffic in probabilities. Because they're countable, we don't break the rules of probabilities. So calculus gives us a way to add up these intervals. And one is the Riemannian sum, which is a precursor to the indefinite integral, and we also have the definite integral. So we're going to use integration, or the antiderivative, in order to put together regions of real numbers, these intervals on the real number line, so that we can build these events for things like the CDF, and now we can talk about probabilities for real value quantities. And so Khan Academy has a great set of modules on the indefinite and definite integrals. I recommend you look at that, and I'm requiring it for this class as a refresher. So here we have our CDF, and the CDF is going to be the antiderivative of the PDF. Said differently, the PDF, which is little f of x, is equal to d dx, the rate of change of the CDF, the cumulative distribution function. And so how you get the CDF is by taking your density and computing the integral over some interval along the real number line. And so the fundamental theorem of calculus tells us how you can take the integral of some function, in our case the density function, between two intervals. It's just the difference of the antiderivatives. And so here we have the real number line, and this real number line, we're going to mark interval for point A, point B, and we want to put together those probabilities. So here's my probability density function. We want to put together all of the probabilities within this interval between A and B. So this is just the probability that random variable x will take on a value that's greater than A and less than B, and it corresponds to mathematically the area under the PDF curve along this interval between A and B. And so fundamental theorem of calculus says, well, we just take that integral, this infinite integral from minus infinity to A, and then integral from minus infinity to B, and we just subtract the two. So this is just the integral from minus infinity to B of f of x dx, and then we subtract from that the integral from minus infinity to A of f of x dx. And so we're essentially taking all of the region from minus infinity to b, and we're subtracting from that all of the region from minus infinity to a. And that difference is the area under the curve for that shaded green region on the slide. All right. And so we compute probability by integrating over a set. Now, the set is an interval on the real number line. And we talk about intervals because we can't identify individual real numbers. If we could, it would be countable and would use summation, but we can't. So we use the integral between those endpoints. Okay, so we have our CDF is the integral from minus infinity to that value b. That's for this endpoint. And then we subtract from that same integral from minus infinity, as we said before, to a. And now the law of total probability is the following. We have the integral from minus infinity to plus infinity. Those are all the values on the real number line. F of x, our density function, dx. And that's just the probability that random variable x takes on a value from minus infinity on the real number line to plus infinity, and that's just 1. So there's our new law of total probability. We use integration to put together regions along, or intervals along the real number line, and we traffic in those instead of individual real number values. Okay, and so let's relate discrete distributions that we have done before. When we did the Poisson, we did the Bernoulli, we did the binomial, we did the negative binomial, we did the geometric, and continuous distributions, which we haven't yet done that. So if the random variable traffics in measurements that are either finite or countable, well, that's a discrete distribution. For the continuous case, the random variable traffics in measurements of observations that are uncountably infinite. Okay. In the case of the discrete case, the countable, well, for the probability, we call it a probability mass function. And for the continuous case, we call it a probability density function. It's really important to know this distinction. They are not the same. Now, if we're building complex events in the discrete or the countable case, we use summation, and we add up all that probability mass over a set of values our continuous, our discrete random variable can take on. But for the continuous case, we use the antiderivative, the integral, over the interval associated with those real values. The real values themselves are uncountable. Okay, and so this is the relationship between the discrete and the continuous, and it's going to be really important that you use the right nomenclature when describing these and understand the differences in how you build the complex probabilities. So you can also have vectors. Before, we said the joint distribution is over two variables, x and y, and we talked about the joint probability table in the discrete case. Now, we have a similar analog for the continuous case. Now, we have the joint cumulative distribution function. So we have big F of random variables x and y, taking values little x, little y, is equal to the co-occurring probability that little x is less than big X, random variable, these are random variables, less than equal to value little x, and at the same time, random variable y is less than equal to little y. Now, when I say less than equal to, that's from minus infinity up to some value x. This is also from minus infinity up to value y. And so here, if we were to look at this joint cumulative distribution, you can imagine here we have, let's say, x. Those are values of random variable x, and these are values of random variable y. And the probability of x and y is along this z-axis. And so if that's the case, well, we know that x can go in the negative infinity direction, y can go off to negative infinity. So we're going the area under the curve from minus infinity up to some value x along the x-axis, and minus infinity up to some value y on the y-axis. And we're just adding up all those probabilities. So if our function here kind of looked like this for our probability density, we're basically adding up computing the volume here for this probability distribution. And that's exactly what this joint CDF is doing. It's the volume from minus infinity up to some value x and up to some value y. And so we can also compute the joint density. The joint density is nothing more than the partial derivative with respect to x and y of this cumulative distribution function for that joint distribution. Now, when we talk about this partial derivative, dx and dy, when we say dx are partial, if we have some function, like say our function was x squared plus y squared, any variable that does not involve x is considered a constant. So this would be derivative of that with respect to x is 0, and this would be 2x. Likewise, if we said dy of that function, x squared plus y squared, well, with respect to y, this does not change at all. That's 0, and then we would have that result is 2y. And so for the joint density, we're taking the double derivative, the derivative with respect to x and the derivative with respect to y. These are partial derivatives of our joint cumulative distribution. And that's our joint density if you have more than one variable. Likewise, if we're going to compute probabilities, now we can take the integral, double integral, with respect to x and y. That's called an area. And that integral with respect to x and y is over the density, the joint density function with respect to dx and dy. Now again, when we do this integral, that's exactly what I talked about before on the previous slide. We're taking the volume here. We have, for example, if we have y and we have x, so that's y and that's x, and we have our axis here is the density, f of x, y, probability density function, and if we have some probability density function, in this case, it looks like a little hump, like a Hershey's Kiss, and if we were to take this probability, well, we're adding up over that volume for some bounds for x and y. We're computing the volume that appears within some region of our defined function. And so you can absolutely compute the probabilities now using this joint density function by integrating over some region of x and y. So for example, if we had this region of y and that region of x, we would be integrating over this area, and that area we're calling A. So that's what it means to compute a probability over a joint density function. We're computing the volume for that density over that particular area. All right. And so independence, when we talked about independence, that definition has not changed for the continuous case. The probability of the joint distribution, x and y, is nothing than the product of the marginals, f of x times f of y. And this is for the density function. We can also marginalize. When we marginalize with the discrete case, we use the summation. In this particular case, we're going to use the integral with respect to the variable that you want to marginalize against. So this is like the summing that we had along the rows and the columns of a joint probability table. And so that means if you have density, joint density function f of x, y, if you want to compute density f of x, that's just the integral of f of x, y, dy. Likewise, if you wanted to compute the density, the marginal density, f of y, that's just the integral f of x, y, the joint density, dx. Okay, and so this is how you marginalize. And now let's look at the summary statistics. We talked about summary statistics, mean and variance, for the discrete distributions, and we developed them for the Poisson, for the binomial, the Bernoulli, the negative binomial, and the geometric distribution. And so our definition of expectation, we said in the discrete case, E of x is equal to, we have the sum over all instantiations of x of P of x. And now instead of using P of x, the mass function, we're going to use the density function, and we're going to use integral in place of the sum because we're dealing with uncountably infinite quantities here. X times P of x, our probabilistic weighted sum. And so here, if we are going to take the mean, that's mu, is equal to expectation. Now we have x, our value, and this is with respect to all values of x, dx. We're going to use integration. And then we take the weighted sum, since weighted by the density. So we have the integral of x times the density function, density of x, dx. And that's going to be our mean, and it's going to be from minus infinity to plus infinity, or all values for which x is defined on the real number line. And the variance, we said, was the expectation of the difference between a random variable, here's a random variable, and its mean, which is up above, e of x. We square it because we care about the magnitude, but not the direction. And so again, we're going to use the density function for our probabilistic weighted average, and we're going to combine these things for the first value of x, the second value of x, third value, and so forth, using the integral. And so here we have all values of x minus its mean quantity squared, weighted by the density function, dx. So we have the integral of x minus mu quantity squared, f of x, dx. Likewise, the covariance. We said the covariance is the expectation of x minus its mean times y minus its mean. That's just, again, we have x minus its mean, y minus its mean, weighted instead of with the joint probability mass function, we have the joint density function. Here's f of x, y. And now we have this integral, it's really a double integral, dx, dy. And that's going to be covariance. And make sure you review example 4.2. That's going to be really, really important. And so these analogs between the discrete distribution for countable random variables and the continuous distribution for uncountable random variables, the difference is in using the density function for the continuous case and using the integral to put them together over the intervals on the real number line. And so there's the difference. Okay, so with that, that's all I had. Again, please make sure you're keeping up with the reading. Make sure you are reviewing those modules from the Khan Academy, because we will use integration and integration by parts directly when we compute the mean and the variance of continuous distributions. So with that, that's all I had. As usual, please stay healthy, please stay safe, and I will see you all